I'm Chris, and I'm going to talk to you about inlining and specialization. So the title of my talk is Inline and Specialized, What Do They Do, and Should I Be Using Them? And for a long time, I didn't have the answers to these questions. I kind of vaguely knew what they do, but I didn't know enough detail about that in order to answer the second question, should I actually use these things in my code? Will they improve the performance of my code noticeably? And usually, when I have something in Scala that I don't understand, I write a talk about it. So that's what I did here, and now I know a lot more than I used to, and hopefully by the end of the talk, you will too. So the talk is in two halves. We'll talk about inlining first, and then specialization after that. So inlining, we'll talk about what it is in general, and then how it works on the JVM, and then more specifically how you do it in Scala. And finally, we'll have a look at a quick benchmark to see how it affects the performance of your code. And then specialization, which I randomly spell with an S or a Z, so sorry about that. First, we'll give a bit of background about why we need specialization, what problem is it solving, and then we'll talk about how it works in Scala, and again, we'll look at some benchmarks. And there's a little warning on the right-hand side. There will be bytecode in this presentation. But don't worry, I'll be gentle, and I will explain the most important bits as we go along. So who am I? I'm Chris. I work at The Guardian in London. We are a newspaper and a news website. I wrote this book. If you're interested in re-engineering legacy software, please have a look. So, the first question you should ask when you agree to listen to me for 45 minutes is, why should I care about this? Why should I bother learning what inline and specialize do and bother putting them into my code? And the answer is that performance matters sometimes. So I came from a Java background. I was writing Java for a long time. And when I was writing Java, performance was a very high priority. It was kind of, it's always at the back of your mind, how is this code performing? Am I using the right data structure? And so on. And then I think that's just part of the nature of the language and the culture of Java. But then when you move to Scala, for me at least, there was a kind of honeymoon period in which suddenly performance is not the top priority. There's things like readability and composability of your code, and you have all of these nice functional primitives like map and filter and so on. And so you're not really that concerned with performance anymore. But then one day there comes a time when you do actually need to write performance critical code. And in those kind of cases, you need to understand how your code is running on the JVM, how does it get compiled down to bytecode, what's it actually doing, and what kind of tools are available for you to improve the performance of your code. So inlining and specialization are two of those tools. So first of all, inlining, what is it? So inlining is a compiler optimization. Basically, it is removing a function call from your code. And it does that by basically copying the function body of the target function into the function that's calling that function. So it's copying the code, the body of the function into the caller. And this happens at the compiler level, or the JVM bytecode level, for example. It doesn't happen at the source code level, but if we look at it in the source code, it looks kind of like this. So on the left-hand side, we have a target function that we want to inline. It's just adding numbers and multiplying them. And then we have a call site, a calling function, which is making a function call to that function. So if we perform inlining on this, then we get the result looks like the right-hand side. We've removed the function call completely, and we've just copy-pasted the code into the call site and obviously updated the variables accordingly. So inlining is a classic compiler optimization. It's been around since the Stone Age. So it's not specific to Scala or even to the JVM. And it has a couple of benefits. Firstly, it removes a function call, and function calls are quite expensive, as we'll see in a second. And secondly, and more importantly, it's an enabler for more optimizations to be done. A lot of compiler optimizations only work within the body of one function. It's quite hard to write optimizations that work across function boundaries. So if you can remove that function boundary and make everything one big function, then you can do a lot more optimizations more easily. And we'll have a look at that in a second as well. So here's our first bytecode. So here is what it looks like to remove the function call overhead. We've got the same sample code as before, but now we're showing the bytecode as well. So before we do our inlining, we have the thing circled in red, this invokevirtual bytecode instruction. And this is the bytecode for calling a virtual function. And this is the thing that we want to get rid of. And you can see on the right-hand side that that call to invokevirtual has disappeared. And the question, obviously, is what's so bad about invokevirtual? So if we have a look at the JVM spec for it, we can see what the JVM runtime actually has to do when you invoke a function. So the first thing it needs to do, if it's a virtual function, is to look up which function you're actually trying to call. Because the function may not be on the concrete class that you're dealing with. It might be on an ancestor of that class. So it might have to walk up the class hierarchy to find the actual function that you're calling. Next, it says a new frame is created on the Java virtual machine stack. So this means there's memory allocation going on here. And if you want to pass arguments into the function, then you'll need to put those onto the stack as well. So that's obviously extra overhead. You have to put stuff onto the stack and then pop it off the stack once you're inside the function. And then thirdly, it says the Java virtual machine PC is set. And here PC means program counter. So this is the pointer saying where the CPU is currently executing, which line of code it's currently executing. So this is basically saying that you are doing a jump. And a jump is kryptonite for your CPU. Because the one thing that the CPU wants to believe about your code is that it's going to keep doing whatever it's doing now. So if you're executing this instruction, and then this one, and then this one, and then this one, the CPU thinks, I spot a pattern here, and it goes and pre-caches a whole bunch of instructions so that it can keep doing this. But then suddenly, you jump over here, and it's got a completely cold cache. It doesn't have any of those instructions already cached, and so it has to go and fetch them. So any time that you do a jump or you somehow do something that the CPU isn't expecting you to do, then it will cause a dramatic slowdown. So we want to avoid function calls. And then the other benefit of inlining, as I explained before, is that it enables more optimizations to be done later. So we have a look at this example. We have a class A that has an xint field, and it has a method +1 that adds 1 to x. Then we have a function that creates a new A and calls the +1 method on it. So step 1, we do an inlining. We inline the +1 and replace it with the body, which is a.x +1. And then this enables a hotspot optimization called escape analysis, which is clever enough to realize that we don't even need to allocate this new A. It's completely pointless. We can just delete all of that code, and it simplifies down to 1 + 1. And then, I haven't checked, but I think since hotspot is smart enough to get to this point, it can probably tell that 1 + 1 = 2. So it probably reduces it even further. So this is just one example, but there's dozens of different optimizations, both in hotspot and in other compilers, that are made a lot easier to do by inlining. So it looks like inlining is quite a good thing. So the big question, obviously, is why not inline everything? Why don't we just inline a whole program into one huge function and then optimize it like crazy? And the answer is that code is data. So every time you inline a function into multiple call sites, it's a duplication of code. Your code size will get bigger. And if your code gets too big, then your working set, your hot code, will no longer fit into the CPU caches, and that will be dramatically bad for performance. So we want to inline as much as we can, but we don't want to make the code too big, so we have to be quite smart about it. Basically, we want to inline hot functions, things that are called very often. And we don't want to inline anything that's not called very often, because it doesn't really matter. And HotSpot is very good at this. It's what HotSpot was designed for. HotSpot, by the way, is the just-in-time compiler for the JVM. And the way it works is that it's continuously measuring how many times each function in your program is being called. And so it's finding the hotspots, the functions that are called a lot, and then aggressively optimizing them. So HotSpot has some heuristics for inlining code. It likes to inline things that are small, things that are hot, called lots of times. And it has a few other heuristics and restrictions as well, but basically small things that are hot. And as you can see here, you have a few JVM arguments that you can use to tweak these heuristics, but the defaults are pretty sensible. As an aside, if you're interested in this kind of stuff, and like me, you enjoy looking at assembly in your free time, then I really recommend this program. It's called JitWatch. It's a really nice open source tool, and it can show you exactly how HotSpot is optimizing your code. It parses HotSpot logs, and it can show you exactly what HotSpot did at each iteration of optimization. So this is Scala Days, but I haven't really talked about Scala yet, so let's remedy that. This is how you do inlining in Scala. We have two annotations available. We have one called inline and one called no inline. And these are hints to the compiler. They're saying, please inline this code if you can, or obviously, please do not inline this code. And they are just hints. So they're not guarantees that this method will actually be inlined. And one thing that a lot of people don't realize is that you have to enable optimization. You have to pass this -optimize flag to the compiler. Otherwise, these annotations will not do anything at all. The inliner is part of the optimizer. So unless you turn on optimization specifically, you won't get any inlining at all. Another nice flag that's worth passing is this -y inline warnings. So this is saying, if you have to ignore my hint, if you don't inline something that I want to inline, please tell me about it. So it'll give you a compiler warning saying, sorry, I couldn't inline this. So the way inlining works right now in Scala 2.11 is quite complicated, I guess. But in 2.12, which I'll describe in a second, everything's going to change. The optimizer has been completely rewritten, so it's a bit simpler in 2.12. But for now, this is how it works. First of all, it will only inline so-called effectively final methods. So this is when you know at compile time exactly which method is going to be called. If it's like a virtual function that could be one of many different concrete implementations, then it's just impossible for the compiler to inline it, because it doesn't know which one to inline. And then it treats your own code, the code that you're compiling right now, as the current compilation, what's it called, like batch of files that you want to compile. It treats those differently from code that's already been compiled. So, for example, your own source code versus some library that you're depending on that's in a jar. So for stuff that's already been compiled, it will only inline things that have been annotated with inline annotation, except for a few special rules, like scala.runtime.star. Everything in that package gets special treatment and things like that. And then it's got these score-based heuristics, which are kind of similar to what HotSpot does. So it looks at the size of the method, the size of the method that's calling that method, and things like that. It also has special treatment for higher order functions and closures, which I will talk about a little bit later. So in 2.12, all of this changes. It's now, the aim is to make it a lot simpler, a lot more deterministic, and so you can easily tell or predict whether the compiler is going to inline a certain piece of code for you or not. So the basic premise is only inline marked methods, and always inline them, including under separate compilation. So now there's no longer this split between your code that you're compiling now and your dependencies. And yeah, I mean, there's basically one rule. If you want to inline it, you annotate it with inline, otherwise you don't. So it no longer looks at the size of the methods or anything like that. But there is one other heuristic that it does, which is to inline higher order functions and closures. So the whole point of this is the aim is better synergy with HotSpot, because HotSpot's very good at inlining, so there's no point trying to do HotSpot's job. But the idea is to use knowledge that we have at compilation time to make life easier for HotSpot. So why do we want to inline higher order functions at compile time rather than leaving it up to HotSpot? We can look at a quick example here. This is a kind of canonical example of higher order functions or closures, I guess. So we've got for I in 1 until 10, println I. So println I is an anonymous function. And then this gets desugared to the version below. So what we're actually saying here is create a new instance of range, create a new instance of this anonymous function that does a print line, and then pass the function into the range.forEach method. And if I'm HotSpot and I'm looking at this code, I have no idea that this is a higher order function that needs to be treated in any special way. It just looks like I'm creating 2 new instances of objects, and I'm passing one into a method of the other. So I might inline it, or I might not. I mean, it all depends on whether it matches those heuristics that I'm using. But in the Scala compiler, we have more information than that. We know that it's a higher order function, so we can treat it specially, and we can do the inlining at compile time. So if we look at how it looks after we inline range.forEach f, and just replace that line with the body of that function, it now looks like this. And then that enables us to do another step of inlining, another iteration of inlining. We can inline the f.applyI. So we replace that with its body, which is just println. And then, if you look carefully, you find that the second line of the function, the val_f line, is no longer needed. It's dead code, so we can just delete that. And so we've completely eliminated this allocation of a new object that we needed in order to pass in our anonymous function. So this is a big win. And this code now looks very, very highly performant. So that's the main reason why we want to do higher order function inlining at compile time. Okay, so let's do some benchmarking. And like most benchmarks in the world, this one is probably wrong in some way. Benchmarking is very difficult, so apologies for that. So when I write benchmarks, I try to make them kind of real-worldy in some way, a bit more interesting than just like a very specific micro benchmark. So in this case, I've chosen to do a fast Fourier transform. In my day job at The Guardian, we don't really do a lot of fast Fourier transforms. But in other domains, obviously, it's very useful. I mean, it's used in MP3 encoding and all kinds of things. I decided to implement the Cooley Turkey algorithm because it has a really cool name. I won't go into the details, but it's a recursive algorithm, so it's quite amenable to a nice functional implementation in Scala. And the meat of the algorithm is lots and lots of numerical operations on complex numbers. So I modeled the complex number with this case class complex, and the point of the benchmark is what happens if I add this inline annotation to my, my complex, my numerical operations on complex numbers. So the moment of truth, here are some numbers. There's quite a lot going on here, so I'll go through it in stages. But first of all, if you compare the the middle column, the left-hand column with the right-hand column, this is the difference between just completely turning off inlining in HotSpot versus leaving it running like normal. And you can see if you enable HotSpot inlining, then the code gets like 3 or 4 times faster. So obviously, inlining is a good thing. We've confirmed that. Second, if you compare, if I can find my mouse, if you compare this row, so this is with the inline annotation, with this one below it, this is where we have a no inline, so we're saying to Scala C, please don't inline this, then you can see they're basically the same. And the reason for this is that HotSpot has inlined it for us anyway, so the whole thing was pointless. And finally, if you look at the difference between the numbers in the top table and the numbers in the bottom table, you can see that just by upgrading to Scala 2.12, we've got, what's that, maybe 10% performance speed up? So that's good news. We can look forward to 10% faster code as soon as Scala 2.12 comes out. And the reason for that, it could be because of the new optimiser, it could be because the higher order functions are now, what are they called? SAMs. I'm not sure exactly, but it's definitely faster. So further reading about inlining, I got a bit carried away here, but there's so much information online about not just inlining, but the internals of the JVM and how the JVM works. Okay, how am I doing for time? Okay, I'll speed up a little bit. Second half of the talk is specialization. So, just a quick refresher on how the type system works in the JVM. We have primitive types, which are booleans and ints and things like that, which are memory efficient. They're not objects, so they don't have the object header overhead, and they can be stored on the stack rather than the heap, and they are passed into functions by value. And then on the other hand, everything else is a reference type. So it's an object, it lives on the heap, and you pass references to that object rather than passing the object itself. I think you probably know all this. So generics. Let's have a quick look at Java, first of all. This is a class in Java that has a generic method foo. It's got the A in brackets saying it's generic in some type A. It doesn't give any kind of bound on it. It could be anything. It could be an int or a string or whatever. And then we call it first with a string, which is a reference type, and then with an int, which is a primitive. And if we have a look at the bytecode for this, at the top, the underlined bit, that says that even though we didn't put any bound on A, it says A has to be an object, which is the ancestor of all reference types. So it's restricted A to being a reference type, which is a bit strange. But this is basically because generics had to be retrofitted onto the JVM later after the fact. So this is the best they could do. And then the bytecode for the test method down below, we can see that encircled in red, we're having to convert our int, our primitive, into a reference type, an integer with a big I. We're having to call this integer.valueOf to convert a primitive to reference type. Can anyone tell me the name of this process of converting a primitive to a reference type? Yes, it's boxing. Rest in peace. And this boxing is obviously bad. It's just overhead that we don't want to deal with. But because of the way the JVM is architected and the way generics is implemented in the JVM, it's kind of unavoidable. So how does this work in Scala? Again, we have this split between primitives on one side and reference types on the other. So all the primitives extend any val, and they are encoded as JVM primitives. And then on the other side, any ref is kind of equivalent to Java lang object. So if we look at some generic code in Scala, here we're using the standard library's mutable map. So we create an empty map with int as its value type. So it's got a primitive as its value type. And then we call it with 123, which is obviously a primitive. We look at the bytecode for this, and we have the same problem. We're calling boxes runtime.box to integer. So whether you're using Java or Scala, you have the same problem, boxing. So how can we get around this? Well, one way of doing it is specialization. So the idea is that you generate multiple versions of a class specialized to each primitive type. So you'd have an int version of your class, you'd have a byte version of your class, and so on. And then, depending on what type you pass into it, when you call the function, the appropriate specialized version of the class would get used. This is how you do it. You just have to add this @specialized annotation to the type parameter of your class. And just by doing that, when you compile it, the compiler will generate all of these 10 or so versions of the class. So here we've got my special map, which is like a mutable map with put and get, but it's specialized, so you can avoid that boxing overhead. So if we have a look at it using this, actually calling some methods on this, it's similar to the sample code before, but now we're using my special map rather than the standard library mutable map. And we instantiate it with int as its parameter type parameter, so it's the int specialized version of the map. We call its put method, passing in 123. And then if we look at the bytecode, now everything's nice and green. We can see that here on line 11, we are pushing a nice primitive integer 123 onto the stack. And then on line 13, we're invoking the function, and we're passing in this thing as an integer. So there's no boxing going on here. So one thing I didn't understand for a while is how does the caller code know that your function or your class is specialized? Say, if I want to put my special map in a jar and publish it to Maven Central, and then you start using it, how does when you compile your code, how does it know that it's specialized and it can call the appropriate specialized class? And the answer is that specialized is a so-called static annotation, which means that that specialized annotation gets stored into the class file for the class inside the ScalaSignature. So in that big blob of binary, if you decode that using the ScalaSignature format or protocol, then you can see that the specialized annotation is actually in there. So the compiler can read that and know, okay, this class is specialized, I'll use the appropriate version of it. So as you may have noticed, there is a space trade-off here. Every time you add specialized to a type parameter, you're generating 10 different classes. And if you do that on 2 type parameters, you're doing 100 classes. 3 type parameters, 1,000 classes. So it's kind of an exponential explosion in the number of classes you're generating. And one way to avoid that is that you can specify exactly which types you want to specialize on. So if you know that my special map will only be used with ints, longs, and doubles, then you can specify that, and that reduces the number of classes that are generated. The problem is, of course, that if you want to publish this as a library for other people to use, it's pretty hard to predict what types people will want to use. And if any of you went to the Dotty linker talk this morning, then Dimitri talked about a way that the Dotty linker in the bright new future will be able to solve this problem for us and do automatic specialization. So that will be really exciting when it happens. So how do things look in the Scala standard library at the moment? To be honest, it's a bit of a mess. So tuple 1 is specialized in int, long, and double. Tuple 2 is specialized in int, long, double, char, and boolean for some reason. Tuple 3 has no specialization, so if you use tuple 3, you get boxing. Option is boxing. Functions 0, 1, and 2 have a kind of random combination of specializations on their various parameters. And then all of the collections classes have no specialization, so boxing. So if you want to avoid boxing, what do you do? There are a few alternatives. There's a library called dbox, and another one called metal, and these both provide mutable collection classes, like map and set and list and so on, but with specialization, so no boxing. And then there is also an alternative approach that's not specialized, so it doesn't use the specialized annotation. It's called mini boxing. It involves a compiler plugin, and it's quite complicated. I won't go into the details here, but it's definitely worth having a look at if you're interested in using the specialization. The idea of mini boxing is that it should give the same speed-ups as specialization, but it results in fewer classes being generated. OK, so just like before, we'll run some benchmarks. We've got two different benchmarks this time. The first one is a Bloom filter. So a Bloom filter is a probabilistic data structure. It's like a set, but it has this query method that will tell you if a certain element is probably in the set. So it returns a Boolean, and if it's true, it means it's probably in the set. If it's false, it means it's definitely not in the set. So in some use cases, this is good enough, and this uses a lot less space than if you were to put all of the elements into a normal set. So it's useful when you have millions and millions of elements. So I've added a specialized annotation on the A type parameter of my Bloom filter. And the point of the benchmark is, does this specialized annotation speed things up? And the results are a bit disappointing. So with specialization and without specialization, it's basically no change. I think the reason is that the Bloom filter is doing quite a lot of other stuff. It's computing hash functions and things, and so the benefits that you get from specialization are just diluted. They're not really that important in the grand scheme of things. So that's a bit disappointing, but let's have another look. Have a look at another benchmark. This is a different data structure. We've got an append-only mutable buffer. So you can append stuff onto the end of it, and then it's got a for each, so you can iterate over all of its content. And the benchmark is to create one of these buffers with 1 million integers in it, and then do a for each, and just loop through all of them. And this time, the results are much more satisfying. We've, just by adding specialization, we have doubled the speed of the code. So that's much better. Again, we've got a bit of further reading. Dimitri's Scala Days talk is in there. Finally, honourable mentions. So this is just a few other annotations that are in the standard library that I discovered while I was writing this talk, and they're quite interesting, but not enough to make a whole talk about. So first of all, we've got strict FP. So apparently, in the JVM spec, you can add a flag to a class file, the strict FP flag, which means make sure that my floating point operations give exactly the same answer on all platforms. No matter where this code runs, I want to get the same answer. So if you don't have that, then you will get more accurate floating point calculations, but they might be different depending on where your code runs. So that might be useful in certain cases. Second is switch. So when you do a pattern match in Scala, that actually gets compiled down to some bytecode, and there's no bytecode instructions for pattern match, so it needs to be lowered to one of a few different statements. So if it happens to be a pattern match on integers, then it can potentially be encoded in bytecode as one of these very performant bytecodes called table switch or lookup switch. And if you want to ensure that's going to happen and your code is going to run quickly, then you can add this switch annotation. And finally, elidable is the weirdest one. So it's an annotation for methods whose bodies may be excluded from compiler-generated bytecode. So you can write your code, you've got your function, but then you add elidable to it, and then when the compiler runs, it just deletes it. It just strips it out. So although I should say, because somebody heckled me about this in New York, there is one good use case for it, and that is to remove the assert statements from the compiler. So it's used in the compiler to, all of the assert statements have this elidable annotation on them, so they get removed completely when the compiler is compiled. Fair enough. So just to sum up, inline is for inlining, obviously. Should you use it? In general, probably not. Just leave it up to HotSpot. It does a pretty good job in most cases. Specialized, should you use it? It depends. It seems to be useful in some cases, but just make sure that you benchmark it and make sure it's actually doing something useful for your code. So that's it. That's my cat, Eric. The slides are online, and the code for the benchmarks is also online. Thank you very much. If you have any questions, then please go to the mics. There's one there and one over there.
You had in your specialized example, you put specialized both on the trait and the class. What was the reason for that?
Sorry, where was that?
Here, just missed it.
On the Bloom filter?
Yeah.
Oh, yeah. So this is, you have to be very careful when you do specialization that you have to specialize all the way down. If you have your function that somebody's calling and passing in a primitive, then you want that to be specialized, obviously. But then if that internally calls another function on the same class or on another class, and you don't have that function specialized, then you will still get boxing at that point. So I haven't shown my implementation here, but when you do an add or a query on the Bloom filter, when you call one of those two methods, then internally it will call the hash function's trait, and it will call a method on there. And so I wanted to make sure that was specialized as well. So you have to be really careful when you use specialized, because it's very easy to accidentally do boxing somewhere in your code. So you end up doing quite a lot of Java P work and checking the bytecode to make sure you are really not boxing.
You mentioned optimize flag for ScalaC compiler.
Yeah.
Do I understand correctly that this flag is only for Scala annotations? So it's not for HotSpot. HotSpot will inline anything what I need to be inlined in runtime, right?
Yes, that is correct. If you want to do inlining in Scala C at compile time, you need -optimize. But HotSpot will always run. Oh, and by the way, it's worth mentioning that optimize, the -optimize flag is a bit suspicious. Like, for example, in the akka official documentation, there's a big red box that says, do not use optimize, it will break your code. So use at your own risk. Okay, looks like no more questions. Thank you very much.